All right, let's get started with the second part of today's lecture. And as mentioned earlier, we will finish our discussion of SAT today. I would like to start with just a few short remarks on a number of topics. Then we will talk about solving SAT using local search methods, which would be a relatively simple discussion, at least from a conceptual point of view. We'll start by mentioning the notion of what people call unsat cores. So the idea here is that if you have a knowledge base that is made up of a number of clauses, let's say alpha 1, alpha 2, all the way to alpha n, and it turns out to be unsat. So people are sometimes interested in finding a subset of clauses that are sufficient to generate a contradiction. So it's possible, let's say, to make it concrete, let's say this is 10 clauses, and it's possible that even though this is unsat, it's perhaps that clause 1 and clause 7 and clause 9 and clause 10 are sufficient to generate a contradiction. That is, you were able to get this to be unsat, and then people would want that. And then you get to the notion of what people call a minimal unsat core, and you can imagine what that is. So not only is this unsat, but if you were to remove any of these 4 clauses, then it becomes satisfiable. So each one of these guys is actually necessary for generating a contradiction. Now, we will leave it at that. There are some maybe rough methods for getting an unsat core in your text, but for us, we'll just leave it at that point. And if there is a question about this, it would be a very small knowledge base. And then you're asked to identify a subset of the clauses that represent unsat core. So I just want you to hear the concept unsat core and minimal unsat core. The other thing I want to comment on, and there is a whole section in your chapter 3 on this, is that implementing unit resolution. We did allude to this earlier, that people have invested in this. Now, unit resolution, even a very naive implementation like the one we're going to mention next and what people start with, will be linear time. But people were not just happy with that. And I'll tell you why. But let's see how, if you were to go and implement now unit resolution, what would you do? So the basic things there is you may have a clause like not A or B, or let's say not D. These would be kind of your clauses, and you may have something like X or C or not E, W, and so on. And the thing that happens with the unit resolution is variables end up taking values, right? So you may have the variable B take the value false. And usually this happens because of 2 things. You make a decision, you say, let me try B equals false, right? This is what we call the decision, or an implication using some other clause. So you may have had another clause that says X or not B, and then because this guy was decided to be false and it got resolved, then you end up concluding that not B is false, right? So you get this, let's call it an implication here, or a setting in various ways. But what happens is, now that you get this guy, so what is unit resolution? It goes to something like this and says, B is false, and this guy says B must be true, so let me take this guy out, and so on. And sometimes if you later get something like D is true, then it will go to this guy and say, oh, D true. This says, okay, let's take that guy out. And then it say now, oh, let me conclude that A is false, and so on. So what people started with is the simple thing. They said, the way I'm going to do this is I'm going to go and have counts with every clause. So when I started with this, the count was 3. Because it has 3 literals, and 1, 2, 3, 4, and this guy has 4 literals. And then what happens is, when I first set this guy and I removed it, so I will make this count 2, because now effectively the clause has only 2 literals. And then when I did this guy, then, and I took this, then basically this guy goes to 1. And this is where I got a unit clause. And then at that point, it says, now that the length has become 1, that means I have inferred something, and dot, dot, dot. So basically, this entails keeping track of these counts for each clause, which is what is its effective length. It also entails keeping track of, for every variable, where does it appear, positively or negatively, because when you set that variable, you want to go to the corresponding clauses and update their counts. And all this can be done in linear time. But again, people were not satisfied with it. Why? Because of learned clauses. So the one thing that maybe we didn't mention is that typically what happens is you end up learning a lot of clauses, because remember, every time you have a failure, you're effectively adding a clause. So typically you end up having a lot of clauses, and moreover, learned clauses tend to be long. They can get very long. So that adds quite a bit of burden. So linear may not be good enough, especially that you have to do this every time you set a variable, which you may end up doing very frequently. So the short story is, people came up with a technique known as too literal watching. I'm just going to mention it briefly, and then you can read the details with a full trace of an example in your chapter. And the basic insight is very simple. And it says, no, I don't have to keep track of the length of every clause. And I don't have to check the clause every time one of its variables is set, right? Because what I just told you, you will have to touch a clause every time you end up resolving one of its literals. Too literal watching says, no, we don't actually need to do this. If you have a certain clause, let's say that, this guy, X or C or not E or W, let's make it even more, or not Z. All you need to do is pick 2 of these literals and watch them, right? So I may pick this guy and that guy. And the idea is, effectively, I can ignore this clause until a change happened to one of these 2 guys. That's when I need to process it. And in your chapter, you will see what is processing in that particular case, because there's a whole bunch of cases you have to consider, few of them, not a lot, and which entail either updating what is being watched, or concluding that the clause has been subsumed, or concluding that the clause has been reduced to a unit clause. All right. So the point is, I designate 2 particular literals in each clause to watch, and that makes things significantly more efficient. And if you look at the details of this method, it has another feature. That when I undo variable, when I unset variables, you basically don't have to do anything. So it's pretty efficient as far as reversing your work, which would be important, because as you know, in SAT solvers, I set and unset and so on. So you can read about this. There is a whole section with a full traced example, but I hope this gives you the basic idea of what's going on. And maybe you can already see why watching only 2 of them is enough. The question about whether unsetting, I mean backtracking, yes, this is when we erase decisions, and therefore we want to undo what we did with unit resolution. Okay, now I have a word on variable orderings and phase saving. And this is effectively a short message here. Variable ordering is the heuristic needed to decide or to choose a variable to try next, right? We've seen that. What should I pick next to try? And that could make a difference. And there you will find 3 different kind of methods, which in your chapter are called dynamic, static, and now I don't remember the term I used for that, which is a combination of these guys. Now, dynamic is what's typically used in SAT solvers. Static and combination were tried, they're not competitive. You would not want to use them for SAT solvers, but they are actually very relevant for the second part of the foundations on knowledge compilation. So that's why I'm hesitating whether to go over these today or leave them till later. But let me tell you the story about dynamic, which is relatively simple. Initially, when people started doing variable orderings, that is picking up what variable to decide next, they were doing methods that try to look at the occurrences of that variable in clauses, right? So they will say variable x, how many times the positive literal x appeared in clauses? How many times the variable, the literal not x appeared in clauses? And they actually even looked further than this. They were looking at things like, what is the length of these clauses? Because remember, if x appears in too many binary clauses, then setting x will end up generating a lot of implications, right? So if you had x or not y, then you go set x to false, then you'll conclude not y, which is viewed as desirable in this particular case. So they were integrating things like how many times did a literal appear in clauses, and integrating the length of these clauses and producing these scores and updating them. And that was expensive, right? Again, each one of these is linear, but then you have to do it a lot, and you have to do it for every variable, and every time you make a decision and simplify the knowledge base. And then later, and this all came also with this Z-shaft solver that I told you, which was a turning point in the history of SAT. Then the idea was, no, let's not do something as expensive as this. Let's do something much simpler, which is simply just look at simple counts of occurrences in clauses on the go with no complicated analysis of what's going on. And let's also do something like, because the thing is when you add these unit clauses that, when you add these, learned clauses that modify the counts, but then the idea was that after a while you start discounting these counts. So you can read about this in your chapter, but the basic idea is with a very low overhead scoring functions, but touching the right thing turned out to be effective. And then people later came up with even more refined ones where they will try to look at occurrence in the implication graphs. And the idea is the implication graph is generating the contradiction, and that's where the activity is. So there were a little bit more pinpointed and focused criteria that were not heavyweight as far as looking at the whole knowledge base, but looking in certain specific places. So you can look at that in your chapter. And I'm going to leave static and combined for now. We'll get to that later. Those are a little bit more conceptually justifiable, perhaps. They require data structures and so on. So that's as far as variable ordering. And the word on phase selection is pretty short here. This is when you pick up a variable x, do you go and try x and then not x, or do you do not x and then x first, right? So this is what's known. And interestingly enough, there is a heuristic that was actually proposed by not Pipastrawat, which I mentioned last time, who wrote the RSAT solver and won the worldwide competition at that time in the industrial benchmark categories. He proposed a very simple phase selection heuristic that's now basically the standard, and that's what everybody implements. And when I tell you what it is, you'll be surprised how simple it is. But it turns out to have a has a significant justification conceptually. In fact, there's a whole paper that was written about why is that a good idea. And I think Donald Knuth, in his volume on SAT, he ended up actually writing about that particular thing. So what is that? It's called phase saving. It's very simple. It says, try the same phase you tried before. So it has a memory of what it tried. Because remember, in this model SAT solvers, you may end up deciding a variable multiple times, right? So you go down, you hit a conflict, you erase, and then you may come back to X and set it again. So what this heuristic effectively has a memory of what it tried before, and it basically tries to use the same phase that it used before. Okay, this looks very simple, and why would something like this be effective, and what kind of analysis, and a whole paper that can be written on this. You can look up the paper by Nutt on this subject. It's pretty amusing to see what's going on. And frankly, it's partly because of the way modern SAT solvers work. This heuristics make a lot of sense. The point is the emphasis now is on heuristics that are very lightweight. You don't want, because you're going to be applying them very frequently, you can't really afford to do even linear work. You need to do something very efficient, and that's where the tendency is in that regard. In fact, the title of the paper for the heuristic by Nutt is called a lightweight component caching scheme. Because the notion or the phase selection heuristic ends up related to some kind of, notion of caching, if you're curious. Okay, folks, this is what I want to say here. The last subject I'd like to cover is on local search, which is conceptually quite different, but as I said, it's relatively simple conceptually, so it shouldn't take us much time to go through that, but still it's pretty important, especially from a practical point of view. Okay, folks, so let me go ahead and get to the last part here on local search. We're going to start first by talking about a connected topic, and that connected topic is random Cnfs. Why is it connected? So as you'll see now, local search methods are methods that solve satisfiability quite differently. They guess a satisfying assignment, and if it is not a satisfying assignment, then they try to modify it, and they just in a very localized fashion, and they keep doing this until they luck out. And the connection to random Cnfs is that there was a time where people wanted to evaluate various algorithms on Cnfs, and they started generating Cnfs randomly. And the story is interesting because they tried something initially, and then there was this suggestion, oh, SAT is easy, and look, we're solving it, except that they found that the Cnfs they're generating were not actually representative. And then there was another method for generating random Cnfs, which became the standard. And for a while, doing local search algorithms was evaluated on these randomly generated Cnfs, to the point that there was even a category of these random Cnfs in the competitions and so on. So let's just have a word first on what happened there on random Cnfs. The first proposal was, I have, let's say, n 100 variables, and let me go generate 1,000 clauses randomly. So what do? You go, okay, first clause, well, I have 100 variables. That's 200 literals. Every variable could be either positive or negative. So you pick up every literal and say, let me include it in a clause with a certain probability. Okay, so you have some kind of probability here of literal appearing in clause. And that's what people did. Okay, so if you do it this way, your clauses will have variable lengths. So you may have a clause with 4 literals, another with 10, and so on. And as I said, people observed that those were easy, but then they realized that's not a good idea because this is not a representative set of Cnfs. And then they came the second proposal, which is what you may want to call so this is fixed length clauses, and this would be variable length clauses. And in this case was, no, you pick up a k, and every clause has length k. And then you basically uniformly choose the literals that appear in that. And this is known as ksat, and the most common is 3sat. So you generate clauses of length 3, and basically you need 3 literals for every clause, and then you generate these uniformly, and that became the standard. And it turns out that those kind of random 3-sats led to some interesting observation. For a little while, everybody was talking about this. And this is, how difficult are these guys? And what people realized is if you look at the number of clauses, right, over the number of variables, you look at this ratio, that gives you a very good indication of how hard these problems are. So, for example, well, let me ask you a question. There are two extremes here. The extreme where this ratio is very small, and where this ratio is very large. What do you think is going to happen when this ratio is very small or very large? So I have very few clauses compared to the number of variables, or I have really a lot of clauses compared to the number of variables. And people are saying if it is small, then it should be easy, right? So the intuition here is that I don't have too many constraints. I mean, you can think of clauses as constraints. I have so many variables, but very few constraints. So that should be easy. And someone, right, underdetermined, so many solutions, very good, correct, Adarv. And yeah, so that would be easy. Now, the other suggestion is what happens when you have too many clauses compared to the variables. Now, one suggestion is it will be hard. And actually, that's not what happened here. It ends up being easy. Can someone suggest why? Oh, right, excellent. Someone is saying because it's most likely unsat, and someone saying overdetermined can possibly have a few solutions or no solutions right, too many constraints right, and then to the point that you can easily detect that. So actually, it was a little bit more interesting. What people found, if you look at it from a probability of SAT, when you get to this end, it's almost 100% SAT. And when you go this way, it is basically 100% unsat. What was surprising is the ratio. You would think this would be too small, this is too large. Actually, 3 and 4 was the kind of cutoffs that when you're below 3 and above 4, so above 4 almost unsat, below 3 almost sat, and these were 4 and 5. And actually, people even found a sweet spot where about 50% of the problems end up being sat and 50% end up being unsat. There were different estimates of that sweet spot ratio. And the one I have in the chapter is 4.24. This was like a magic kind of a ratio of clauses to variables, where about 50% of the problems were sat and the other unsat. And those are the problems that were viewed as the most difficult in terms of doing satisfiability on them. So here it was getting easy, here it was getting easy, and this is where things were difficult. And typically when people talk about generating random 3-sat, they're generating ones according to this ratio. There was a while where there was a lot of emphasis on these guys, as I said, to the point where there is even tracks for random sat. I don't think this is happening now. There was discussions at some point is how useful it is to build SAT solvers that are doing well on these kind of problems. So you'll see now different kind of categories in these competitions. So there is an industrial category, there is handcrafted, where people handcraft difficult problems and so on. Okay, let's now go and talk about basically the basic ideas of local search algorithms. And it's more of a family of methods. And so we'll go over the basic concepts and give you a sense of some of the variations. The short story with these methods is which one works is a matter of what kind of problems you have, and they involve some fine-tuning. They all tend to have what we would call hyperparameters, things that you have to tune. But the basic idea is pretty simple, that you would make a basically guess to start with, which is a variable assignment, All right, so you may go ahead and say, let me try A equals true, B equals false, C equals true, dot, dot, dot. Okay, and let's call this a W. And you try it out. And if it's not, then you try to modify it. And here's where it gets into the notion of local search. Local search more generally, and this is a style of solving problems that's not just specific to SAT. You have this candidate that you're looking at, and you have these neighbors, which are, so if this is a world, this would be what other worlds I can try if this doesn't work. And these basically notion of neighborhood usually is defined depending on the problem. So in SAT, typically the neighbor is obtained by flipping one of the variables. Okay, so in this case, if I go ahead and say, okay, let me make this B equals true, that would be one neighbor, and which means if I have n variables, then every node will have basically n neighbors, because I can just flip one of the n variables. Okay, so this is the first concept. It's like if I'm here and then it doesn't work, then I can go to one of these guys. And then I'm here. If it doesn't work, then I go to one of these guys. Now the question is, so this is guess and neighbors. The question is, what do I do? Which one do I pick? And this is the notion of a move, which is how do I select a neighbor to go to? And here you have variations, but it's typically what's involved is the notion of a cost function. And in this case, you're trying to satisfy. So you look at the number of clauses that are satisfied and try to maximize that, or sometimes people look at the number of clauses that are unsatisfied and try to minimize that. In your text, that's what's happening. So this is number of unsat clauses and then minimize. Okay, so as far as using that, again, here things can get quite interesting. Is how do I use this to make a move? And there are different variations and they lead to different algorithms. And I'll just mention one of the simplest one, and then I'll mention a few of variations. The simplest one is what you'd expect. So if you are here and the cost is not zero, that means there are some clauses that are still unsatisfied. Then what you do is you look at your neighbors and you compute the score of each one of them. And you try to go to the guy that has the lowest score, right? So if you're here and you're unsatisfying 15 clauses and one of your neighbors will only unsatisfy 9, then you go to that. You go to the lowest, the one with the lowest. So this is like one of the simplest ones. What then gets you to the question of, so what happens if none of my neighbors are better than me, right? So I'm satisfying unsatisfying 15, but then I look at every neighbor, they're doing worse. What do I do in that case? And this is where basically you get into this third category of things that control behavior, which is termination criteria. So this is called, the one that I just mentioned, sometimes known as hill climbing. Okay, that's better when we're maximizing, but it's the same thing. And when none of your neighbors are better, well, the simplest thing is to give up and say, that's it. Now, that's not too good, right? So you may have guessed something and immediately your neighbors are not better than you, then you just give up. And this is where you have this, key notion of restarts. So there is a notion of I give up temporarily and I give up globally, right? So there's two notions of give up in a sense. One of them, like we've just seen, where you look at your neighbors and say none of them are better, then let me give up. But then you go to another level which says, okay, let me try another guess altogether and repeat this process. And that's known as a restart. And typically people say, okay, I'm going to do like 1,000 restarts. So, get started, guess something, go local search, and if you get stuck in what we call a local minima in this case, then let's do a restart. But if I did 1,000 of them, then I give up. That's global give up. Okay. All right. So let's talk now about that's basically the overall structure. What we're going to do is just talk a little bit about the variations here. as far as how do you make a move, right? But otherwise, the overall structure is similar. In fact, in that part of your chapter, there is one piece of pseudocode for all of these methods. And we'll just talk about some of the variations here and just a couple of variations, and that will basically be it. And again, just before I forget that there are variations. You will see they do have hyperparameters, some of them, and you'll have to fine tune these. And the earlier works, when people were very active doing this, there was a lot of papers saying, oh, this is the best way to do this. This is the best way to do that. And they'll turn out to be not too founded. They were basically, those observations were specific to the benchmarks that people have tried, but it's not as easy to make very general conclusions about these methods. Okay, let me talk about a couple of these variations. And those, again, you will hear this story more broadly beyond SAT. When people did it in the context of SAT, they gave them names. One variation is, at that time, people call it GSAT. And the idea is that this was just exactly like we did with hill climbing, with one difference, which is the notion of a side move. So if you're here at this guy and you look at your neighbors, and they all are worse, but maybe some are exactly like you. They have the same score as you. What do you do in that case? Do you end up going there, which would be called a side move or not? And it turns out to be, this is very significant. You would want to make side moves. So GSAT was this kind of hill climbing with basically side moves. And then there was another variation, which is called WalkSat. And this was under a family of what people call Iterative Repair. So what this guy did was a little bit different in the sense that when you are, let's say, at W and your score is 15, that means there are 15 clauses that are unsatisfied. So what you try to do is you pick one of these clauses and try to fix it and to satisfy it, right? So if you had one of these clauses and it was A or not B or C, and it's already not satisfied, this is one of the 15, what does that tell you? That tell you your current world is setting this to false, setting this to true, and setting this to false. It must be that way for this to be falsified. Then you flip one of these guys. Now, you may have choices of which clause that you do randomly. If you have a clause now, then you may, which one of these three do I flip? You may want to look at what other clauses it actually fixes. And when you have choices, you have to do, you can do things randomly. And here, let me inject one important thing. So this is basically what this does. It tries to direct the movement to a neighbor with the idea of trying to fix certain clauses. Now, what happened here is when you look at what's going on, you'll see you will have choices. And there is a tendency to do one of these things. Like you say, okay, which one of these variables should I pick to flip? Because any of them will fix this clause and make it satisfied. So there's two tendencies here. One of them is to go and say, let me pick the guy that will fix other clauses. And the other thing is to say, let me do it random. And it may be tempting to say, no, let me go and pick the guy that actually fixes more clauses. And here we see this tension in these algorithms between, as you're making choices, trying to think logically and optimize certain score versus introduce enough randomness in the algorithm. And randomness actually helps a lot. So sometimes if you go too far with making your choices go towards optimizing things, the algorithm end up getting stuck. And one of the arts of doing these algorithms so that they actually work well is to have the right combination of direct your choices towards doing something specific versus make them random. And the very last thing that I'm going to mention, which is just a couple of words, and you can see the details in your chapter, which is simulated annealing, gets more on the side of the randomness part. But before I get to that, let me mention that the main characteristic of these methods, maybe you guys can, one of you can tell me, what do you see one big feature of these methods compared to what we looked at? Okay, there is the randomness, but give me a positive thing, a concrete positive thing as far as using resources. what do you think the space complexity of these guys are? Negligible, right? As far as space complexity. You basically need to know where you are. You don't have a memory. They're very modest in terms of memory and space. And the other thing you need to know, there's a deficiency compared to the previous ones we looked at. The major thing compared to the other methods we looked at. Are these even guaranteed to find? No guarantees, exactly. They're not even guaranteed to find a satisfying assignment if one exists. And they have a particular problem proving unsat, right? I mean, if you've searched for 3 days and you didn't find a solution, do we know it's because there is no solution, or you just didn't visit enough of them? As far as completeness with respect to finding a solution if one exists, if these guys are designed carefully in terms of injecting enough randomness in the right place, you can issue a guarantee that eventually they will find a solution if one exists. And basically, people have to prove that eventually every possible variable assignment will be visited with a probability greater than 0. And there you see the role of randomness. So let me say a word on simulated annealing. At a very high level, simulated annealing looks a little bit surprising. When it's at a particular node, it will pick a neighbor randomly. So it's at this node, and this node is not it. So it will pick up a neighbor randomly. If it betters, it goes there. If it's not better, it will go there with a certain probability. And this probability looks like this. I'm going to write it. It's going to look weird, but I'm going to explain it. So once more, your neighbor is better, go there. Your neighbor is worse, go there with some probability. There are two things that contribute to this probability, the delta and the TI. The delta is how worse it is compared to you, right? So if your neighbor is, the more worse it is compared to you, this guy, what happens to it? It goes higher, and this probability will go lower. So you are less likely to go to a neighbor as it gets way worse than you. This is one thing. So what is this other guy, T sub I? This is known as a temperature. It is a number that kind of gets smaller as you try more. So I is how many moves you've tried so far. And the idea is, as you have tried more and more, this number gets smaller. So what does it mean for this number? If this number gets smaller, this whole probability also gets smaller. So the idea is, you pick up a neighbor randomly. If it is better, just go there. If it's worse, go there with a certain probability that depends on two things: how bad it is and how long have you been searching. So if you just started searching, you're more willing to take bad moves. But as time goes on, you're less likely to do that. And this curve here is one of these hyperparameters. It's known as a temperature schedule. You choose one. There is a whole bunch of things that people propose there, but that's basically the idea. And then you can combine this with restarts as well, so you can, try this a number of times. All right, folks, this is what we needed to say for today. We pretty much finished our chapter on a discussion of satisfiability. There's one more topic, not on satisfiability, on MaxSat, and then we bridge. So this is like the first hour of Tuesday, and then we bridge to another world of foundations. The one thing I want to mention is we invested so much in these techniques because even though they were done under the label of SAT, they're actually broadly applicable. So even when we go to more complex approaches and more far-reaching approaches based on knowledge compilation, SAT is NP. The next thing we're going to be targeting with these techniques are much complex classes, PP, NP to the PP, like probabilistic reasoning, machine learning. Even though the foundations are different, everything we've done here is at the core of how these things work. So this investment is not just for SAT. This investment is broadly applicable. And again, that's it for today. Thank you, everyone. And I will see you on Tuesday.